Day and welcome to today's training on chilled water systems part 1. This is a fairly long training session, so I'm going to break it up. There's quite a bit to digest. So I'm just quickly setting a thing or two up here and then we can start. Okay, chilled water system configurations. When designing a chilled water system, a number of decisions must be made. Experienced engineers often make these decisions on past experiences. Some guys even just use Google. But in today's times, most engineers likely use the internet to get direction. But when there are differing or conflicting recommendations, a decision must be made. There are many possible chilled water configurations. Each chilled water configuration has its own advantage and disadvantage. Designing a proper chilled water system is a must to reduce your initial operating and maintenance costs and to guarantee proper operation of the chilled water system in both air conditioning and industrial cooling applications. So what are some of the things that we need to look and decide at? Well, common deciding factors would be a bypass line sizing for systems designed with variable flow designs, dynamically varying condenser water flow rates. So when you see the word dynamically, it always refers to something that's moving, okay? The number of chilled water pumps that we need to operate. Do we connect the chillers in series or parallel? And what is our power consumption going to be? Is there a budget for redundancy? Most times, more than likely not. It's very prudent to always design with redundancy. And then what control valves do we use to control the working fluid, the water? So if we just look at a few chilled water components, we obviously have the chillers, air-cooled, water-cooled. We have pumps, hydraulic connectors, thermal inertia tanks. Big fancy word. It's pretty much a chiller where you store your chilled or your hot water. It stores thermal inertia. We have fan coils. We have 2- and 3-way modulating valves. We have water filters, shut-off valves, and expansion tanks. Obviously, we need expansion tanks with all chilled water operations. They are primarily there to stop any expansion of water in the event of water getting hot. And also when pumps and that suddenly stop, there's a nitrogen bladder in here and it prevents a lot of water hammer. And because water can't be compressed, you'll end up blowing flange gaskets, you'll end up rupturing elbows and bends on your line. So these tanks absorb any dynamic loading from a sudden shut off and they prevent water hammer. So heating and cooling sources and loads. Our chiller is the source and our load can be a cooling or a industrial process that needs cooling. And here we typically see a heating or cooling source, which would be our chillers providing heating or cooling. And here is the load. It could be process cooling, it could be comfort or office cooling, and obviously you need a pump to circulate the working fluid. Let's break this down a bit now and let's look at the load side. The load is dealt with through water-cooled terminals or fan coils, or could be big air handlers, and needs to be controlled in order to maintain the exact temperature in the spaces to be air-conditioned under varying conditions. The designer must determine what method will be used and how it will impact on the control of both the fan coil unit as well as the hydraulic implications on the plant. The basic control methods are generally always the same. You have sensors They measure the actual sensible conditions and give feedback. So they'll measure air temperature, water temperature, and give feedback. The control system, which is the brains, then compares the feedback and makes judgment against the set conditions. So those are your set points. The control system will make judgment and make the various changes. And then we have the temperature and or the water flow rate, which is to be adjusted to match the changing loads in the spaces. Types of control methods on the load. So how do we control the working fluid? Well, besides moving it around with pumps, we have a three-way modulating control valve, two-way modulating valves, and face and bypass damper control. Not very, not as popular as fan coils, but I will show you the working principles of face and bypass damper control. If we have a look at a three-way control valve operation, here's typically your fan coil unit. So a three-way valve is one method, is the three-way valve, to control the flow of chilled water through the cooling coil. As the space cooling load decreases, the modulating valve directs less water through the coil, and now then will decrease the coil's capacity. The excess water bypasses the coil, so excess water is going to flow through here now, and it's not going to flow through the coil, okay? And mixes downstream with warmer water, which already went through the coil, so it's going to mix downstream of the valve. The temperature of the return water decreases as the cooling load of the space decreases. That sort of makes sense. The flow goes through the load when the valve is in position A/B. Okay. And here we see the cool air. I'll show you. So when the valve is modulating through A and B, A/AB, it's going to allow water purely to go through the load. Port B now will be closed, so the water is going to go there and it's got nowhere to go. It's going to stop there. As the valve moves from position A/AB to B/AB, some water will now bypass the load and flow through the bypass line. So this is your bypass line, and you're going to get some water going through here and some water going through there and mixing downstream. At the end of the stroke, port A of the valve is closed and all the water will flow through B/AB. Okay, there will be now no water flow through the load. So there's an electric motor that drives a valve stem, and it will open this fully if the load has reached its temperature and no water will flow through. Now it's going to hit there. All the water is now going to bypass. There will be no flow through the load. A three-way mixing valve has the same effect on the load as a two-way valve, but not hydraulically on the system. We'll get a bit to that soon. So here we can have a look. I've put these arrows in, and here's your bypass loop. So constant water volume in the shape of a square. So imagine this is a constant water volume. The green line will be bypassed water, and these blue lines will be going through the fan coil unit. Interesting to note there's constant volume here. Okay, no matter what happens, this square will always, let's say it's 2 centimeters by 2 centimeters, will always measure 4 square centimeters of area, and times that by the length of volume. So there's a constant volume going through a three-way valve. This linear line indicates the valve position of the valve stem moving in and out. It's linear, okay? So this is pretty much what a three-way control valve looks like. Your actuator motor, electrical motor, will be on 12 volts or 220 or 24 volts. So what is the working principle? I've put here we need an actuator to drive the valve stem. The return water flow from the fan coil, which is the sum of the water flowing through the coil and the bypass water flow, is constant water volume in all operating conditions. Due to this constant volume, pressure waves or water hammer are eliminated during valve modulation. You may have come across this if you shower or if you close your taps at home very quickly. That's like a two-way valve principle. Your pipes will bounce in your roof. This won't happen with a three-way valve because of the constant water flow. The return water temperature varies as a function of the space cooling node. This isn't always a good thing though, okay? So you have constant water flow, but your return water temperature is going to vary. Pump energy is constant at all loads, so it's advisable to use a fixed speed pump here. You don't want to vary water volume because it's a constant volume valve. So it's no real sense in putting a variable speed pump on it using three-way valves. Very importantly, water balancing is critical to obtain proper operation due to the constant flow rate. Here you can see a disadvantage of bypassing water. So imagine your fan coils here. So if I bypass 100% water, is that the return water temperature remains almost the same temperature as the supply water. This can cause the so-called low delta T syndrome. Big fancy word, but more on the low delta T syndrome later in the training course. If we look at a two-way valve operation now, excuse me, a two-way modulating valve is similar to a three-way modulating valve. It modulates the water flow through the cooling coil in response to the load requirements. The primary difference is in the case of a two-way modulating valve is that unused water is not bypassed. It simply throttles the amount of water passing through the coil. Excuse me. As the valve modulates in proportion to the load, the water quantity flowing through the coil goes from design flow to no water flow at all. Importantly, there's a time delay between 100% and 0%, which takes about 2 minutes of full operating load. A two-way valve is mainly used in large applications and bigger systems where frequency-driven pump is installed to vary the general water flow. So we don't really use constant water flow pumps here. And here we can see the water volume varies proportionally in a function to the load. This white area indicates that no water is bypassed. So you see the volume is constantly, this is the only volume of water. It's different to the previous three-way valve that had constant water volume in the square. So there's no constant water volume. So two-way valve control, that's pretty much what a two-way valve looks like. What is the working principle? The return water temperature is relatively constant. Bear in mind, we're talking temperature, not volume, regardless of the space cooling load. When a decoupled line is installed with a pressure regulating valve, the water flow through each terminal varies proportionally in a function of the load. So here we're not changing temperature, we're changing water flow rate. The pump energy varies proportionally in a function of the load. So that's inverter-driven pumps. A variable flow system is less sensitive to water balancing when compared to constant flow systems. So it's far more forgiving because we're constantly modulating and changing the flow rate of water. A variable flow system may require another method to provide constant water flow to the chiller or chillers, or the chiller should be provided to handle variable water flow, but a bypass line with a pressure sensitive valve. In general, a two-way valve is recommended because it modulates the water flow proportionally to the load. That's where thermal inertia tanks also get important. So if we have a look at this example, the fundamental differences between two and three-way modulating valves. Here's a two-way valve, here's a three-way valve. The fundamental difference between the two-way valve and the three-way valve is that the chiller sees the load. The two-way valve provides a variable flow, load response, and a three-way valve provides constant flow. So the three-way valve provides constant flow with a varying temperature, whereas a two-way valve provides variable flow with a constant temperature. So these two are different. The temperatures vary and the mass flow rates vary. As the load changes, in the case of the two-way valve, the water flow will vary while the delta T is fixed. In the case of a three-way valve, the delta T varies while the water flow rate is fixed. So generally for big applications, we use two-way valves, and for small applications, we prefer to use three-way valves. The other way of control I mentioned was face and bypass damper controls. If we look at this typical air handling unit, we'll see here air bypasses cooling coil, and this is the face, bypass and face damper control. You will see here that it sucks in a big volume of air, goes over a fan, we force a draft through, we aim the damper blades up, and here the bypass is down, and we destratify the air, and the thermostat picks up the supply air with the dampers, and the stats then control the angle of attack on these damper blades. So another way to control the cooling and heating capacity of a single zone system is to use face and bypass control, sometimes also referred to as mixed air control. In this case, the capacity is controlled by a set of two damper mechanisms. There's the one damper mechanism and there's the other. Face dampers are located in series with the cooling coil and or heating coils, while bypass dampers are not in series with the coil. You can see they're not in series. Okay. The dampers selected are called parallel blades, as can be seen below. All blades are at the same angle at the same time. The bypass and face dampers work together, but as opposed blade damper systems. So here's an opposed blade damper system, and here's a parallel blade. A room thermostat will modulate the positions of the two dampers to mix proper amounts of airflow through the cooling coil, as well as the bypass path. As the cooling load decreases, the face damper will close, which is this face damper, reducing the airflow across and therefore reducing its capacity. At the same time, the interlinked bypass damper opens, allowing more air to bypass the coil. The water flow through the coil is constant, so you've got constant water flow. You don't really play with this flow rate. All you do is you control the dampers. So face and bypass damper control, what's the impact on the system? The return water temperature will vary as a result of the space cooling load, and the water flow through each terminal is constant regardless of the load. This results in obviously using more pump energy. So summarizing, we have three different control methods: the three-way, the two-way or the face bypass. The water flow is constant through three-way modulating valve, variable through the two-way, and constant through the face bypass. Just picture the two-way as you'll say like a tap at home. What effect does it have on return water? Well, a three-way is variable, fairly constant on a two-way, and variable on a face and bypass damper. When properly designed, operated and maintained, any of these three systems can result in good space temperature control. However, they have different impacts on the chilled water system. The use of a three-way modulating valve and face bypass dampers results in variable return water temperature and relatively constant chilled water flow through the entire system. The use of a two-way modulating valve, on the other hand, results in relatively constant return temperatures and variable flow through the entire system. Before choosing one of these control methods, it's very important that the designer determines the effect his choice will have on other components of the chilled water system. Now that we looked at the production or the control side, now let's look at the production side. That's obviously where we make the chilled water on the chillers. So first of all, we have evaporator water flow. We have two types. We have constant water volume and variable water volume. Constant water volume through the evaporator is the most common. It's more stable, as well as a simpler chiller and simpler chiller design and simpler system operation. Variable water flow, however, big energy savings are possible. Okay, the big thing people forget is the operating cost of a chiller plant. You might save on the initial outlay of doing a constant water design, but chillers can run into hundreds of thousands of rands operating expenses, pumps, cooling towers, variable fan speeds, all of that. It requires advanced chiller and system controls though to vary the water flow rate. The majority of chiller manufacturers used to promote a constant evaporator water flow. However, even in the most carefully designed chilled water systems, the flow through chillers will vary due to system effects such as pump and system interaction, dynamic head variations, and variations in distribution system flow. There are many benefits to maintaining a constant water flow through the chiller evaporator. Constant water flow provides a more stable and simpler chiller and system operation. However, there's potential for huge energy savings by varying the water flow in the distribution system. Applying these seemingly conflicting principles, and they are rather conflicting, to chilled water system requires careful planning and a thorough understanding of hydraulic system operations. Due to advances in technology, many of today's chillers can operate with variable evaporator water flow. This is also where it comes down, where you have flow switches and anti-flutter relays, because the biggest problem varying evaporator flow rate is freezing on the evaporator, and we do have offsets on our chillers, I think up to 30 seconds, where you will have flow switch flutter until we get stabilization. But as I've said here, due to advances in technology, the systems are a lot more tolerant to varying water flow through evaporators. So let's look at a simple single chiller supplying water to the load. The load could be air handlers, it could be fan coils, chill beams, or even big process equipment. The pump type will depend on the control valves used. So if we choose 2O valves, variable volume, or 3O valves, constant volume. A single master pump circulates chilled water, and a standby pump can be provided, like I've drawn here, duty standby. We can control either on return or leaving water temperature. Now, one or multiple chillers in a system. In most cases where loads exceed 4 to 500 kilowatts, the use of multiple chillers is common. Redundancy provides reliability, or the balance of reliability and cost. The most typical system configuration by far is 2 chillers. However, as cooling loads usually vary, multiple systems can quite easily operate with less than the full number of chillers on the process. During these part load conditions, there's an energy savings due to the non-operation of the additional chillers, pumps, and in the case of water-cooled systems, we have cooling tower fans. Let's look at some possible configurations to connect multiple chillers in these different systems. So let's look at this simple design here. 2 chillers in parallel with only 1 pump. This configuration can be used in systems that use constant flow control methods, so 3-way valves and bypass dampers, or in a system which uses variable flow control method with a 2-way valve. Varying the flow through the load, okay, not through the chillers, but through the load terminals, using the 2-way valves will result in variable water flow through the evaporator and chiller. So that's a very important thing to remember, okay. The water is pumped through the 2 chillers continuously through the single pump, okay, regardless of whether one or both chillers is operating. In this example, the system is at 50% load if one chiller is operating and the other one is switched off. Return water continues to flow through the non-operating chiller. So the 12 degrees comes in. Because this chiller is not running, it's still going to pump 12 degrees out. The return water continues to flow through the non-operating chiller and mixes downstream with the chilled water produced by the operating chiller. The resulting mixed water temperature leaving the cooling plant is now higher than designed. So you can see here I'm mixing with 7 degrees and I'm coming out with an example of 9.5 degrees water. This rise in supply temperature may result in problems with building comfort and humidity control. A chiller plant controller may be used to lower the set point of the operating chiller in an attempt to compensate for the increased mixed leaving water temperature. So if we have a sensor here, chiller plant controller might try and drop this now to 5 degrees to maintain the 7 degrees that we want here, okay? But there's implications. Reducing the set points of the operating chillers has its limits. It depends on the operating characteristics and the evaporator freezing limits of the other specific chillers. The more chillers in the system, the more this is going to become a problem. For this reason, this configuration isn't used much. It's seldom used in systems with more than 2 chillers at very low part load conditions. It's better to rather reduce the water flow in order to increase the energy savings. So now let's look at parallel chillers with separate pumps. So here we have separate pumps per chiller. If separate dedicated chillers are used, the chiller and its pumps can be cycled together. This solves the flow mixing problem, but now presents a new problem in the system that uses constant flow method of the terminal control. So if we make this drawing look a little bit more complicated, with only one pump chiller operating, the total system water flow will decrease significantly according to the pump system curve relationship. Okay. All the load terminals will now receive less water regardless of their needs. Typically, some coils will receive full water flow and others little or no water. In either case, heavily loaded coils will usually be starved for flow rates, which could become problematic in spaces which have constant heavy loads, example computer rooms, conference rooms, etc. If we have a look at the pump curves for these pumps, the diagram shows an example of a pump system curve relationship. When both pumps are operating, the system receives 100% of the design flow. So here you can see 100%. Pump 1's run, and I switch pump 2 on, and the system curve, and I drop that down. So that's my head pressure I require to overcome losses. Also the height of the building, I need to pump a head pressure. And with both pumps running, I reach my sweet spot, and I reach 100% of my design flow. When only one pump is operating, the intersection of the pump's performance curve now with the system curve results in about 65% now. Don't just automatically presume it's going to be 50%, okay? So technically I run one pump, I'm only going to get 65% of the design flow. This configuration also presents problems to the chiller operation. The starting or stopping of a pump for one chiller affects the flow through the other chiller. Using this example, if one chiller is operating and a second chiller and pump are started, the water flow in the system doesn't double. Okay, very important. Don't think that the water flow is going to suddenly double. The system and pump performance curves will rebalance, resulting in an increase in the system flow of only 35% of the total flow. The new total flow, however, is now divided equally between two chillers. This results in a rapid reduction of water flow through the original operating chiller from 65% of the total now down to 50%. Important to remember that. Eh? This rapid decrease in flow often results in a loss of temperature control and may cause the chiller now to shut off on a safety due to low flow to prevent freezing. In order to overcome this problem, the chiller plant control system should anticipate the starting of additional pumps and unload the operating chillers prior to the starting of an additional chiller. The system configuration is sometimes acceptable for two chiller systems, but not often used in large systems because of the part load system flow problems. What this is pretty much saying is instead of just starting or switching off a second pump, start unloading the chiller that's operating and then bring on the other pumps. It's going to stop this low delta T and thermal shock due to the reduced water flow rate. Let's now look at chillers in series with one pump. Notice these chillers are now pumping into each other. They're not in parallel and they have one pump pushing water through both chillers. When chillers are pumped in series, the mixing problem disappears, as well as the starving coil problem. However, the flow rate through the individual chillers is equal to the entire system flow rate. When we compare this configuration with parallel chillers configuration for the same delta T, there will now be twice as much water flow through each chiller. This means that chiller tube pass arrangement must accommodate double the water quantity with an acceptable velocity and pressure drops. Remember, you increase the velocity, you also increase the pressure drop. This typically requires a reduced number of passes in the evaporator and may have an impact on chiller efficiency. You'll notice that some of Daikin's new chillers only have a single pass in and out. They don't have the curved double passing. The system pressure drop will increase because the pressure drop through the chillers is additive. So if you have 20 kPa here and 20 kPa, the additive loss is 40 kPa. This will lead to an increase in the pump size now, and we'll have to consequently have an impact on the energy consumption. This increase in pumping energy can be substantially reduced if the system is designed for a higher delta T and therefore reduced water flow. However, efficiency loss is more than offset by increased chiller efficiency because the upstream chiller, well, now here's the upstream chiller, it will operate at warmer temperatures. Because of the pressure drop limitations, it's difficult to apply more than 2 chillers in series. Systems involving 3 or more systems typically use either primary, secondary configurations or parallel sets of 2 chillers in series. We'll get onto that as the training gets more and more advanced. Let's have a look at a live example with 1 pump and a return water of 15 degrees. Temperature control in a series system configuration can be accomplished in several ways, depending on the desired operating sequence. In the above configuration, the chiller set points are adjusted to the desired supply water temperature. So here we've set both of them to 7 degrees. Assuming equally sized chillers, keyword is equally sized chillers, either chiller can meet the load below 50%. Above 50%, both chillers operate, and the upstream chiller, which is the first receiving chiller, is preferentially loaded. This means that the upstream chiller is operated at full capacity at any portion of the load that remains, any portion of the load that remains is handled by the downstream chiller. So this chiller will run at 100%, and this will assist to bring the final water down to 7 degrees. This configuration, where would we use it? Well, it can be maybe desirable in systems that benefit from preferential loading by preferentially loading the upstream chillers. Examples include using a heat recovery chiller in the upstream position. Alternatively, equal loading of the 2 chillers in series can be accomplished using a chiller plant control system to monitor system load and balance chiller loading. The set point for the downstream chiller is set equal to the desired supply water temperature, and the set point for the upstream chiller is then dynamically reset to maintain equal loading on both chillers. This is obviously done by the chiller control system, and the chiller control system must be stable enough to prevent control and hunting of the chiller cycling during periods of changing load. That's the last thing you want, is up and down hunting effect. Let's rather look at this example now with chillers in series with 1 pump with staggered set points. Notice this is the chiller set at 11 and the second chiller is now set at 7. An alternative method of controlling chillers in series involves staggering the set points of the 2 chillers. This results in the downstream chiller operating first. So we operate this chiller first and being preferentially loaded. Any portion of the load that the downstream chiller cannot meet is handled now by the upstream chiller. During part load conditions, when using 3-way valves, the temperature returning to the chillers decreases. The return water temperature may, example, be 13 degrees instead of 15 degrees at 100% design load. In such a case, the upstream chiller, which is the upstream chiller, may be partially loaded, cooling water down to 11 degrees, while the downstream chiller will remain fully loaded, cooling the water the rest of the way to 7 degrees. And that is where I'm going to end this training session. You can go over and digest, and the next training session is going to be primary and secondary configurations, hydraulic water flow conditions. I hope you enjoyed the training and re-watch it and get yourselves up to speed. Till we meet again. Ciao.